For much of modern history, the universe felt immense, but ultimately contained. Vast beyond ordinary comprehension, yet still described with boundaries, numbers, and timelines that suggested a complete picture was possible. There was a beginning placed roughly 13 to 14 billion years in the past, a sky filled with hundreds of billions of galaxies, and a sense that the observable cosmos, while enormous, was still something that could be measured and understood. That picture did not collapse all at once. It began to erode quietly as deeper observations replaced darkness with structure. Regions of space that once appeared empty revealed faint traces of distant light. What had looked like gaps between galaxies slowly filled in, not with isolated points, but with layered populations of stars and entire galaxies stacked behind one another across immense distances. When the James Webb Space Telescope began observing the universe in infrared light, that erosion accelerated. Webb did not simply sharpen what was already known. It exposed what had never been visible before. Ancient light, stretched by the expansion of space itself, emerged from regions long assumed to be close to empty. In those depths, the universe did not appear tentative or unfinished. It appeared active, crowded, and unexpectedly mature. Galaxies emerged far earlier than long-standing models predicted. Some were already massive. Some were already forming stars at intense rates. Black holes appeared in epochs where there should barely have been time for them to grow. The early universe, once imagined as slow and fragile, revealed itself as luminous and productive almost from the start. Yet the most profound implication of these discoveries is not simply how early structure formed or how quickly complexity emerged. It is what these observations reveal about scale itself. The deeper Webb looks, the closer it approaches a boundary defined not by technology, but by physics. There exists a limit to what can ever be observed, a horizon set by the age of the universe and the way space expands. Beyond it, galaxies continue to exist, stars continue to form, and cosmic history continues to unfold. But no signal from those regions can ever arrive here. Not because the light is too weak, but because the space between grows faster than any message can cross. The universe that can be seen is not the universe in its entirety. It is a window shaped by time, expansion, and the finite speed of light. James Webb has not shown the edge of existence. It has shown how narrow the view has always been. To understand what these observations mean, it helps to set aside the idea that space is something we simply look across. In the universe, distance and time are inseparable. Every beam of light carries with it a record of when it began its journey. Looking outward is never an act of seeing the present. It is an act of reading the past. Light moves at a fixed speed, fast by any everyday standard, yet limited on cosmic scales. Even nearby distances introduce delay. Light from an object a short distance away reaches the eye moments after it leaves its source. Light from the moon arrives several seconds late. Light from the sun reaches Earth minutes after it was emitted. These delays are small enough to go unnoticed, woven quietly into daily experience. As distance increases, delay grows with it. The nearest stars beyond the sun are seen as they were years ago. The center of the Milky Way appears as it existed tens of thousands of years in the past. When observation extends beyond the galaxy itself, time stretches into millions and then billions of years. The universe begins to reveal itself not as a single moment, but as a layered record of earlier states. On these scales, the night sky stops behaving like a snapshot. it becomes an archive. Each point of light represents a different chapter, captured at a different moment in cosmic history. Nearby objects show the universe in its current form. Distant objects reveal what it once was, long before planets formed and long before stars like the Sun existed. This effect grows even stronger because space itself is not static. The universe expands, and as it does, it stretches the light traveling through it. Wavelengths lengthen as space grows, shifting energetic blue and ultraviolet light into red, and eventually into infrared. This stretching is known as redshift, and it provides a direct measure of how long light has been traveling through an expanding universe. The greater the redshift, the longer the journey, and the earlier the moment of emission. Redshift turns light into a cosmic clock. It allows astronomers to look not only far away, but deep into the past, tracing how the universe changed across billions of years. Earlier telescopes were built to observe primarily visible and ultraviolet light. This narrow window matches the range human eyes evolved to detect and works exceptionally well for studying nearby stars, nebulae, and galaxies. But as astronomers pushed farther back in time, the universe slowly slipped out of view. Ancient galaxies did not disappear. Their light moved beyond what those instruments could register. James Webb was designed to observe the universe where that missing light now resides. Its instruments are tuned to infrared wavelengths, capable of detecting radiation that has by ends stretched almost to invisibility by cosmic expansion. To achieve this sensitivity, Webb operates far from Earth, shielded from heat and light, cooled to temperatures where even faint infrared signals can be measured. When Webb observes regions that appear completely dark to the eye, it is not searching for emptiness. It is waiting for photons that have traveled for billions of years, crossing an expanding cosmos and carrying information from eras close to the universe's beginning. Each detected photon marks the end of a journey that began when the universe was a fraction of its current age. What emerges from these observations is not a quiet, gradual beginning. It is a universe already filled with activity. Galaxies appear at times when theory predicted only scattered stars. Structures show organization when there should have been little time for it to develop. The early universe does not unfold slowly into complexity. It seems to accelerate toward it. This realization reshapes how scale is understood. Distance no longer means separation alone. It becomes a measure of time elapsed and expansion endured. Looking deeper does not simply extend vision outward. It pushes observation closer to a fundamental boundary set by how long light has been able to travel since the beginning. That boundary defines the observable universe. It is not an edge in space, but an edge in information. Beyond it lies a vast continuation of reality that exists without ever being seen from here. And as observations approach that limit, the question of how large the universe truly is begins to take on a very different meaning. At first glance, the size of the universe seems like a simple calculation. If the universe began about 13 to 14 billion years ago and light travels at a fixed speed, then the most distant objects should lie roughly that many light-years away. For a long time, this intuitive picture shaped how the cosmos was described. But intuition fails once expansion is taken seriously. The universe is not a static arena through which light moves. Space itself stretches. When distant galaxies emitted the light now being detected, they were far closer than they are today. Over the billions of years that light traveled, the space between its source and its destination continued to grow. By the time the light arrived, its point of origin had been carried far beyond where the journey began. This is why the observable universe is much larger than its age might suggest. The most distant light reaching Earth today began its journey when the universe was very young, but the regions that emitted it are now far farther away than the light's travel time alone would imply. Accounting for this expansion leads to a surprising result. The radius of the observable universe is not around 14 billion light-years. It is closer to 46.5 billion light-years, making the full observable diameter roughly 93 billion light-years. This vast size is not theoretical speculation. It follows directly from measurements of cosmic expansion and the way space has evolved over time. Light did not simply cross a fixed distance. It traveled through a universe whose scale was continuously changing beneath it. Early in cosmic history, expansion was slower, allowing light to make steady progress. Later, expansion accelerated, stretching distances more rapidly. The journey became more difficult, not because light slowed down, but because the destination kept moving away. This creates a horizon, not a physical boundary or a wall in space, but a limit defined by time and expansion. Light from beyond this horizon has not had enough time to reach Earth, and in many cases never will. Space between those regions and here expands too quickly for signals to ever arrive. This does not mean the universe ends at that horizon. Observations suggest the opposite. In every direction, the universe appears remarkably uniform. There is no sign of an edge or a center. The faint afterglow of the early universe looks nearly the same across the entire sky. That uniformity would be impossible if space abruptly stopped just beyond what can be seen. Instead, the observable universe is best understood as a sphere centered on the observer, defined by how far information has been able to travel. Move to another location in space, and the observable universe changes. New regions come into view, while others slip beyond reach. Every point in the universe defines its own horizon. This leads to a subtle but profound consequence. Two distant galaxies can both be visible from Earth, yet unable to observe each other. Light from each can reach here, but light from one may never reach the other. There is no privileged viewpoint from which the entire universe can be seen at once. James Webb has pushed observations closer to this horizon than ever before. When it detects galaxies at extreme redshifts, it is capturing light that began traveling when the universe was only a few 100 million years old. Those galaxies are now far beyond where that light originated. Their later evolution, their mergers, and their transformations lie beyond reach, locked behind the expansion of space itself. What is observed is not what exists now. It is what once existed, preserved in light. And even that record is incomplete. Beyond the observable horizon lies a vast expanse of unobservable universe, regions that may contain galaxies, clusters, and structures as rich and complex as anything seen, yet permanently hidden. As this realization settles in, another implication emerges. If the portion of the universe that can be observed already spans 93 billion light-years and contains more structure than expected, then the total scale of existence may be far larger than once imagined. And that scale becomes impossible to ignore once Webb begins counting how many galaxies actually inhabit the observable cosmos. For much of the 20th century, astronomers believed they had a reasonable grasp of how galaxies formed. After the universe cooled from its earliest hot state, matter was thought to drift almost evenly through space. Small irregularities existed, regions that were slightly denser than average, but gravity was expected to work slowly. Over hundreds of millions of years, gas would cool, collapse, and ignite the first stars. Galaxies would begin as small, faint systems and only gradually grow larger through quiet accumulation and occasional mergers. This picture implied a gentle beginning. The earliest universe should have been sparse and dim, with only a handful of fragile galaxies appearing within the first few 100 million years. Bright, massive galaxies were expected to be rare until much later, after gravity had time to build complexity step by step. When James Webb began surveying the early universe, that expectation was quickly challenged. Instead of isolated primitive systems, Webb found crowds of galaxies appearing far earlier than predicted. Many were already large. Many were already forming stars at intense rates. Some were bright enough to be detected even if they were far more distant than they already were. This created an immediate tension. Brightness implies mass. Large numbers of stars are required to produce that much light, and stars do not form instantaneously. They require time to assemble, to ignite, and to evolve. Seeing such luminous galaxies so early suggested that the universe was building structure far more efficiently than existing models allowed. The problem was not limited to a few unusual cases. Across multiple surveys and independent observations, Webb continued to detect early galaxies that appeared too massive for their age. Within the universe's first 500 million years, systems containing hundreds of millions or even billions of stellar masses were already in place. According to conventional timelines, there simply had not been enough time for gravity to assemble so much material. Even more surprising was what Webb's spectra revealed about these galaxies. Their light carried signatures not only of hydrogen and helium, the elements formed shortly after the beginning, but also of heavier elements such as carbon and oxygen. These elements are forged inside stars and released only when stars die. Their presence meant that earlier generations of stars must have already formed, lived out their lives, and enriched their surroundings, all within a remarkably short span of cosmic time. This discovery suggested that the universe did not ease gradually into complexity. It surged toward it. Star formation appears to have proceeded at extraordinary rates, transforming gas into stars with an efficiency rarely seen in the modern universe. Astronomers began referring to this mismatch as the problem of too much light too early. When theoretical models predicted how much total starlight should exist in the universe's first billion years, the numbers fell short. Webb's observations exceeded those predictions by factors of several. This was not a minor discrepancy. It indicated that key assumptions about early cosmic conditions were incomplete. Researchers examined every possible source of error. They checked whether dust could be amplifying brightness. They considered whether gravitational lensing might be magnifying distant galaxies. They questioned whether black holes at galactic centers could be contributing extra light. Each factor helped explain part of the excess, but none resolved it entirely. In some cases, the galaxies appeared so massive that astronomers briefly labeled them universe breakers. According to standard cosmology, systems of that size simply should not exist so early unless something fundamental about galaxy formation was missing. One proposed explanation involved efficiency. The early universe was denser than it is today. Gas clouds were packed closer together, collisions were more frequent, and cooling may have occurred more rapidly. Under these conditions, star formation could have proceeded faster than in modern galaxies, where feedback from stars often disrupts further growth. Another possibility involved mergers. In the crowded early universe, galaxies interacted and collided more often. These encounters can drive gas inward, compressing it to extreme densities and triggering intense bursts of star formation. Instead of slow, steady growth, galaxies may have built much of their mass in short, violent episodes. None of these ideas alone fully resolved the discrepancy. They reduced the tension, but did not eliminate it. And at the centers of many of these early galaxies, Webb revealed another challenge entirely, one that pushed existing theory even further. At the heart of many of these early galaxies lies an even more unsettling discovery. James Webb has identified black holes already in place when the universe was only a few 100 million years old. Some of them possess masses millions or even billions of times greater than that of the Sun. Their existence at such early times poses a serious challenge to conventional ideas about how black holes grow. Under standard physics, black holes begin as the collapsed cores of massive stars. These initial remnants are relatively small, typically only a few tens of solar masses. From there, growth occurs through the gradual accumulation of surrounding gas and through mergers with other black holes. However, this growth is not unlimited. As matter falls inward, it heats up and releases radiation that pushes outward, slowing the rate at which additional material can be absorbed. Even under ideal conditions, this process takes time. Building a black hole with a mass of 1 billion suns should require far longer than the early universe appears to allow. Yet Webb continues to find such objects in epochs when, according to existing timelines, they should not yet exist. This has forced astronomers to consider alternative pathways. One possibility is that some black holes did not form from stars at all. Instead, enormous clouds of gas may have collapsed directly into black holes, bypassing the stellar stage entirely. This would allow much larger initial masses and accelerate growth dramatically. Another idea involves the first generation of stars themselves. In the early universe, stars formed from nearly pure hydrogen and helium, without heavier elements to regulate cooling. Under these conditions, stars may have grown far more massive than those seen today, reaching thousands of times the mass of the Sun before collapsing directly into large black holes. There is also the role of mergers. In the dense, early universe, black hole collisions may have been far more frequent. Repeated mergers could rapidly build mass, especially within crowded galactic centers where gravity pulls matter inward efficiently. Each of these scenarios stretches current understanding, but none can be dismissed outright. What makes these early black holes particularly important is not just their existence, but their influence. As they accrete matter, they release enormous amounts of energy. That radiation heats surrounding gas, regulates star formation, and alters the evolution of entire galaxies. Together with intense star formation, these black holes transformed the early universe. Their radiation contributed to the reionization of cosmic gas, stripping electrons from hydrogen atoms and changing how light traveled through space. Their gravitational pull shaped the flow of matter, helping to build the first large-scale structures. If galaxies and black holes formed earlier and more efficiently than expected, then the entire timeline of cosmic evolution shifts. Events once thought to occur gradually may have unfolded far more rapidly. This realization forces a reassessment of how quickly the universe can organize itself under gravity. As Webb continues to observe deeper regions of space, this pattern becomes harder to ignore. The early universe was not a slow, tentative environment. It was energetic, efficient, and surprisingly mature. Structure appeared quickly, and complexity emerged almost as soon as conditions allowed. This acceleration has implications that extend far beyond individual galaxies or black holes. If the universe could assemble large structures so early, then the scale of what exists today, billions of years later, may be far greater than previously imagined. And that implication becomes unavoidable when Webb turns from studying how galaxies formed to answering a simpler but far more consequential question. How many galaxies are there? For decades, astronomers believed they had a workable estimate of how many galaxies existed. The approach was simple in principle. A telescope would be pointed at a tiny, seemingly empty region of sky. Every visible galaxy within that patch would be counted. That number would then be scaled up to represent the entire observable universe. When the Hubble Space Telescope carried out its deepest observations, the results were astonishing for their time. In a region of sky no larger than a grain of sand held at arm's length, thousands of galaxies appeared. From these counts, astronomers concluded that the observable universe contained on the order of a few 100 billion galaxies. It was a staggering figure, and for years it stood as a symbol of cosmic abundance. James Webb changed that estimate almost immediately. When Webb revisited similar deep fields, the difference was unmistakable. Where earlier images showed darkness between galaxies, Webb revealed faint infrared glows. What once looked like empty space resolved into structure. Smudges turned into galaxies. Gaps filled with light. The universe, it seemed, had been hiding far more than previously realized. The reason for this discrepancy was not oversight or error. It was limitation. Many distant galaxies emit light that has been stretched by cosmic expansion far beyond visible wavelengths. That light slipped past earlier instruments unnoticed. Webb was designed specifically to detect it. In one of its deepest surveys, Webb observed a region of sky that appears insignificant to the naked eye. Over many hours of exposure, it collected thousands of individual images and combined them into a single, extraordinarily detailed view. The result contained hundreds of thousands of distinct galaxies, layered across vast distances and spanning nearly the entire history of cosmic time. Each point of light in such an image represents not a star, but a galaxy. Each galaxy contains millions, billions, or even trillions of stars. Many host planetary systems. Many contain environments where chemistry becomes complex. The universe revealed by Webb is not sparsely populated with isolated islands of matter drifting through darkness. It is densely packed, structured, and active at every scale. What makes this discovery even more powerful is that Webb does not merely count galaxies, it measures them. By analyzing their light, astronomers can estimate distances, masses, star formation rates, and ages. This allows the reconstruction of how galaxies evolved across billions of years, transforming static images into a dynamic history. From this reconstruction, a clear pattern emerges. Galaxies are not distributed randomly through space. They gather along vast filaments, intersect at dense nodes, and avoid enormous regions almost entirely. On the largest scales, the universe resembles a complex web, with strands of matter stretching across space and enormous voids opening between them. This structure is known as the cosmic web. It formed from tiny fluctuations in density present shortly after the universe began. Regions that were slightly denser than average exerted slightly stronger gravitational pull. Over time, matter flowed into these regions, amplifying the contrast. Dense areas grew denser. Sparse regions emptied further. James Webb's infrared vision has revealed this structure with unprecedented clarity. Many galaxies hidden by dust or distance now appear clearly along these filaments. Entire populations of star-forming galaxies fill regions that once looked empty, revealing how matter organized itself on the largest scales. Some of these structures are vast. Chains of galaxies stretch millions of light-years across, already well-formed when the universe was only a few billion years old. In some cases, galaxies within these structures have already stopped forming stars, suggesting that dense environments can accelerate a galaxy's life cycle, pushing it toward maturity far earlier than expected. Yet alongside this richness lies profound emptiness. Between the filaments of the cosmic web lie enormous voids. These regions span tens to hundreds of millions of light-years and contain very few galaxies. They are not small gaps. They are the largest structures in the universe by volume. If one could exist within the center of such a void, darkness would extend in every direction for immense distances before the nearest galaxy appeared. Entire regions of space failed to accumulate matter simply because gravity drew that matter elsewhere. This contrast between crowded filaments and empty voids reveals a fundamental truth about the universe. Matter was never evenly distributed. From the earliest moments, gravity sculpted space into a landscape of concentration and absence. As Webb's deep field observations accumulated, astronomers began revising their estimates once again. If these dense populations of faint galaxies are representative, then the observable universe may contain not hundreds of billions of galaxies, but trillions. For every galaxy once counted, many more may have gone unseen until now. This revision carries staggering implications. More galaxies mean more stars. More stars mean more planetary systems. More chemical diversity, more opportunities for complexity to arise. The universe revealed by Webb is not just larger in size, it is richer in content. And yet, even this abundance exists only within the observable universe. Beyond that boundary, space continues. Structure continues. Galaxies form and evolve in regions that can never be observed from here. Webb has shown that even the portion of reality we can see is far more crowded than expected, which leads to an unavoidable realization. If so much exists within the narrow window of observation available to us, then the true scale of the universe beyond that window may be far greater than imagination allows. As the scale of the observable universe comes into focus, another force moves quietly into the foreground. One that does not build structure, but steadily pulls it apart. The expansion of the universe is not slowing down. It is accelerating. When cosmic expansion was first discovered, it was assumed to be a fading echo of the universe's beginning. Everything was moving outward, but gravity acting over billions of years should gradually slow that motion. Whether the universe expanded forever or eventually collapsed back in on itself was an open question, but gravity was expected to dominate the long-term outcome. That assumption did not survive careful measurement. By observing distant stellar explosions with predictable brightness, astronomers found that galaxies were receding faster now than they were in the past. Space itself was expanding at an increasing rate, as though driven by a force acting against gravity on the largest scales. To account for this behavior, cosmology introduced a new component, one that could not be seen directly, but whose influence was unmistakable. This component became known as dark energy. Dark energy does not emit light, absorb radiation, or clump into objects. Its presence is inferred entirely from how it affects the expansion of space. Measurements indicate that it accounts for most of the universe's total energy content, vastly outweighing ordinary matter and even dark matter combined. What makes dark energy especially strange is how it behaves as the universe grows. As space expands, the density of matter decreases. Spread the same amount of matter over a larger volume and it becomes thinner. Dark energy does not follow this pattern. Its density remains nearly constant even as space stretches. This creates a feedback effect. As the universe expands, the total amount of dark energy increases. That additional dark energy drives faster expansion, which creates more space, which in turn produces more dark energy. Over time, this process comes to dominate cosmic evolution. Early in the universe's history, matter was dense enough for gravity to shape structure. Stars formed, galaxies assembled, and the cosmic web emerged. But as expansion continued and matter spread thinner, dark energy gradually overtook gravity on the largest scales. Several billion years ago, this transition became decisive. Expansion began to accelerate. James Webb does not observe dark energy directly, but its influence is woven into every deep observation. The extreme stretching of ancient light, the enormous size of the observable universe, and the growing separation between distant galaxies all reflect its presence. This accelerating expansion carries a profound consequence. The observable universe is not a fixed region. It changes with time. Light from distant regions continues to arrive, slowly expanding the boundary of what can be seen. But at the same time, expansion is pushing distant galaxies away faster than light can cross the growing gaps. The result is a universe where visibility is temporary. Galaxies that are observable today will not remain so forever. As space stretches, their light shifts to longer wavelengths, fading gradually from detectability. Eventually, new photons from those galaxies will never reach Earth. From this perspective, the cosmic horizon is not merely a boundary of the past. It is a boundary of the future. Regions of space that are now part of the observable universe will one day slip beyond reach, not because they cease to exist, but because expansion carries them away faster than information can follow. If the behavior of dark energy remains unchanged, the long-term future becomes stark. Over tens of billions of years, galaxies outside the local gravitationally bound group will disappear from view. What remains observable will be a small island of stars surrounded by darkness, with no visible trace of the vast cosmos that once filled the sky. This has a strange implication for cosmic perspective. Observability depends on time as much as location. The universe that can be seen today is not the universe that could be seen in the past, nor the universe that will be seen in the future. Each moment defines its own horizon. James Webb sharpens this realization by showing how close present observations already are to that boundary. Many of the galaxies it detects exist at distances where their future light will never reach Earth. What is observed is not a continuing story, but a single preserved moment. The universe revealed by Webb is not just immense. It is fleeting in visibility. Most of existence lies either beyond reach already, or will soon become unreachable as expansion accelerates. And this realization forces attention toward an even deeper question. What force is powerful enough to shape the universe's fate so completely, while remaining almost entirely unknown? While dark energy governs how the universe expands, it does not explain how matter organizes itself within that expanding space. For that, another unseen component plays an equally essential role. One that does not push galaxies apart, but instead binds them together and gives structure to the cosmos. This component is dark matter. Dark matter does not emit light, absorb radiation, or interact with electromagnetic forces in any detectable way. It cannot be seen directly. Yet its presence is revealed through gravity, again and again, across every scale of observation. Without it, the universe revealed by James Webb could not exist in its present form. The first clues emerged long before Webb. Astronomers studying spiral galaxies noticed that stars in their outer regions orbit far too quickly. According to the visible mass alone, those stars should escape into intergalactic space. Instead, they remain bound, moving as if surrounded by vast amounts of unseen matter. The same problem appears on larger scales. Galaxies within clusters move too rapidly to be held together by visible matter alone. Gravitational lensing reveals distortions in background light that require far more mass than stars and gas can provide. In every case, the conclusion is the same. Most of the universe's matter is invisible. Roughly 85% of all matter consists of dark matter. Ordinary matter, everything from galaxies to planets to living beings, makes up only a small fraction of what exists. What gives dark matter its power is not just its abundance, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself or lose energy through radiation. It moves through space, almost frictionlessly. This allows it to begin clumping very early in cosmic history, long before stars or galaxies could form. Shortly after the universe began, tiny variations in density existed throughout space. Dark matter responded to these variations first. While ordinary matter remained hot and resistant to collapse, dark matter began gathering into invisible concentrations known as halos. These halos grew steadily under gravity, forming the scaffolding of the universe. As the universe cooled, ordinary matter fell into these dark matter wells. Gas collected, compressed, and eventually ignited stars. Galaxies did not form randomly. They formed where dark matter had already assembled, chasing an invisible blueprint laid down billions of years earlier. This process produced the cosmic web. Vast filaments of matter stretching across space, intersecting at dense nodes where galaxy clusters formed, separated by enormous voids. What appears as a pattern of galaxies in the sky reflects a deeper structure defined by dark matter alone. James Webb's observations have brought this structure into sharper focus. By detecting faint and distant galaxies that earlier surveys missed, Webb fills in missing segments of the cosmic web. Filaments that once appeared broken or incomplete now appear continuous, revealing how early matter began organizing itself on the largest scales. These filaments are not static. Matter flows along them. Gas streams toward dense regions, feeding galaxies and clusters. Growth is guided, not random. Even the Milky Way resides on one of these filaments, connected by invisible pathways to larger structures drifting through space. In recent years, astronomers have detected dark matter directly along these filaments using gravitational lensing. Light from distant background galaxies bends slightly as it passes through regions where filaments are predicted to exist. The distortions are subtle, but consistent. They reveal mass where no visible matter can account for it. This confirmation transformed the cosmic web from a theoretical framework into an observed reality. The universe is not a loose collection of galaxies drifting apart. It is an interconnected network, held together by invisible matter. At the intersections of filaments lie galaxy clusters, the most massive gravitationally bound structures in existence. A single cluster can contain hundreds or thousands of galaxies, vast reservoirs of hot gas, and enormous amounts of dark matter. These clusters act as anchors, pulling matter inward over billions of years. When galaxies fall into these dense environments, they change. Gas is stripped away. Star formation slows or stops. Structures become smoother and more uniform. Webb has observed these transformations in detail, capturing galaxies in the act of being reshaped by their surroundings. Yet for all its influence, dark matter remains deeply mysterious. Its composition is unknown. It may consist of particles beyond current physics or involve phenomena not yet imagined. Decades of experiments have searched for direct detection without success. And still, its gravitational signature is undeniable. Remove dark matter from the equations, and the universe falls apart. Galaxies could not form. Clusters would not exist. The cosmic web would dissolve into a nearly uniform fog of matter. James Webb does not solve the mystery of dark matter, but it strengthens the case for its central role. By revealing how quickly structure formed in the early universe, Webb shows that an invisible gravitational framework must have been in place from the beginning. And yet, even this invisible skeleton operates within a universe dominated by dark energy. Dark matter builds structure. Dark energy stretches space. The cosmos exists in a constant tension between these two unseen forces. As the full picture comes into view, one final realization emerges. Everything observed, galaxies, filaments, clusters, even the cosmic web itself, exists only within a narrow window defined by time and expansion. Beyond it, the universe continues unseen. Billions of years ago, the observable universe was smaller. Fewer regions had time to send their light across space. As time passed, more distant light arrived, and the boundary expanded outward. In that sense, the observable universe has been growing since the beginning. But this growth hides a deeper contradiction. While more distant regions slowly come into view, the expansion of space itself accelerates. Distant galaxies are not simply far away. They are being carried away faster and faster by the stretching of space between them. These two effects compete, and the result is a universe where visibility is temporary. Some galaxies whose light reaches Earth today will not remain observable forever. As expansion continues, the space between here and those galaxies will grow faster than light can cross it. Their images will freeze at a particular moment in cosmic history, then fade as their light stretches beyond detectability. Eventually, no new information from them will ever arrive. From a long enough perspective, the observable universe becomes a shrinking archive. Not in size, but in content. The number of galaxies within view decreases, not because they disappear, but because they slip beyond the cosmic horizon. What remains visible grows increasingly local. If dark energy continues to behave as current measurements suggest, the far future will look profoundly different. Observers billions of years from now would see only a small cluster of nearby galaxies bound together by gravity. Beyond that island of light, space would appear empty and still. Those future observers might never suspect that the universe was once filled with distant galaxies, vast filaments, and deep cosmic structure. The evidence would be gone, stretched away by expansion. The universe would appear small, static, and isolated, not because it is, but because visibility has narrowed. This realization reframes the meaning of cosmic scale. The universe does not present itself all at once. It reveals different portions at different times and hides others permanently. What can be observed is not a complete inventory of existence, but a time-dependent sample shaped by expansion and perspective. James Webb sharpens this awareness by pushing observation closer to the horizon than ever before. Many of the galaxies it detects exist at distances where their future light will never reach Earth. What is seen is not an ongoing story, but a preserved moment, frozen by the limits of physics. This is why Webb's discoveries feel unsettling. Not because they contradict known science, but because they expose how narrow the window of observation truly is. Even with the most advanced telescope ever built, most of the universe remains inaccessible, not hidden behind distance alone, but behind time itself. The universe revealed by Webb is crowded, structured, and astonishingly rich. Trillions of galaxies may exist within the observable region alone, each containing billions of stars, each embedded in a vast cosmic web shaped by invisible matter. Yet all of this represents only a fraction of what likely exists beyond the horizon. There is no reason to believe that reality changes abruptly beyond what can be seen. The same processes that operate here likely operate there. Galaxies form, stars ignite, black holes grow, structures assemble, and cosmic history unfolds, all beyond reach. The true scale of the universe, then, is not defined by the furthest galaxy ever observed. It is defined by the gap between what exists and what can be known. James Webb has not closed that gap. It has illuminated it. By showing how much structure exists near the edge of observation, Webb forces a confrontation with scale that is no longer abstract. The universe is not just larger than expected. It is larger in a way that makes complete knowledge impossible. Every observation is bounded. Every deep field is a narrow tunnel through time. Every measurement reveals only a slice of a much larger whole. And that may be the telescope's most important contribution. Not the discovery of individual galaxies or black holes, but the realization that the universe cannot be fully surveyed, mapped, or contained within any frame of reference. What exists is vastly greater than what can be seen. One of the most counterintuitive consequences of cosmic expansion is that the observable universe is not a shared object. It is not a single sphere everyone agrees on. It is personal to location. Every point in space defines its own observable universe. From any other galaxy, the horizon would be centered there, not here. Some regions visible from Earth would lie beyond reach from elsewhere, while other regions invisible to us would fall within view. There is no universal vantage point from which the whole cosmos can be seen at once. This has subtle but profound implications. Two distant galaxies can both be observable from Earth, while remaining permanently invisible to one another. Light from each reaches this location, but the space between them expands too rapidly for their signals to ever meet. From their perspectives, this region may lie beyond their own horizons. In this way, the universe fragments observationally without fragmenting physically. Reality remains continuous, but knowledge does not. What can be known depends on where and when observation takes place. This removes any notion of a central position. No galaxy sits at the middle of expansion. No location is favored. Every observer sees distant galaxies moving away in all directions, not because they occupy a special point, but because space itself is stretching uniformly. The familiar idea of scale breaks down here. Distance alone no longer defines separation. Time, expansion, and perspective intervene. A galaxy that appears extremely distant may once have been much closer. another that appears nearby may soon slip beyond reach forever. James Webb highlights this by observing galaxies whose light began its journey when the universe was still young, but whose present state is unknowable. Their stars may have aged, merged, or vanished. Their structures may have transformed completely. That information is already lost to expansion. Observation becomes asymmetric. The past remains accessible while the future recedes. Light arrives carrying history, but no return signal is possible. In this sense, the observable universe is weighted toward memory. This reframes how scale should be understood. The universe is not simply large, it is layered. Different epochs overlap within the same sky. Different distances correspond to different times. What appears together visually never existed together physically. The cosmos becomes less like a place and more like a record, assembled from fragments of different eras. James Webb does not photograph the universe as it is. It samples the universe as it was, across a vast range of moments stitched together by light. This understanding dissolves many intuitive assumptions. There is no single age visible at once, no single scale, no complete map. Every deep observation is partial by definition. What remains is a universe that cannot be fully grasped from any position, no matter how advanced the technology. Not because of ignorance, but because of structure itself. Seen this way, James Webb's true contribution is not a list of discoveries, but a recalibration of perspective. It does not simply add detail to an existing picture. It changes the frame entirely. The universe is larger than once imagined, not just in size, but in consequence. It formed structure earlier, assembled matter faster, and contains far more galaxies than previous surveys suggested. Yet even these revelations apply only to the portion of reality that happens to be observable now. Beyond that region, the universe continues without interruption. There is no indication that physics changes abruptly at the horizon. The same processes likely unfold there as they do here. Stars ignite. Galaxies collide. Black holes grow. Cosmic history advances, unseen. The boundary that limits observation is not a wall in space. It is a condition imposed by time and expansion. It is not something technology can overcome. No telescope, no matter how powerful, can observe regions whose light will never arrive. This places a fundamental limit on knowledge, not a practical limit, but a physical one. The universe allows observation, but not completeness. It offers access, but not totality. James Webb makes this limit visible by showing how much structure exists near the edge of observation. The closer observations move toward that boundary, the clearer it becomes that most of reality lies beyond it. Scale, then, is not a number to be memorized. It is a relationship between what exists and what can be known. The observable universe, immense as it is, represents only a temporary cross-section of a far larger whole. What is revealed is not just distance, but constraint. Not just abundance, but inaccessibility. The universe is not only vast, it is partially unreachable by design. And yet, within that limitation lies something remarkable. From a small region of space, at a specific moment in cosmic history, it is possible to infer the existence of far more than can ever be seen. Patterns repeat. Laws remain consistent. Structure scales. James Webb does not close the story of the universe. It opens it outward, beyond observation, beyond completion, beyond final answers. What it ultimately reveals is not the true size of the universe, but the true scale of mystery itself. Seen from this wider perspective, the James Webb Space Telescope does not simply extend human vision. It exposes the limits built into observation itself. The universe it reveals is not just larger than expected, but structured in a way that prevents complete access from any single place or time. The observable universe, immense as it appears, is only a temporary cross-section of reality. Its boundaries are shaped by the speed of light, the age of the universe, and the accelerating expansion of space. What can be seen today is different from what could be seen in the past, and different again from what will be visible in the future. There is no indication that the universe changes abruptly beyond the cosmic horizon. The same physical laws appear to operate everywhere. Observation is possible. The same patterns of structure repeat across vast distances. Galaxies cluster along filaments. Matter gathers where gravity allows. Emptiness opens where it does not. These patterns strongly suggest continuity far beyond the limits of visibility. In that sense, the horizon does not mark an edge of existence. It marks an edge of information. Beyond it lies a universe that continues without ever announcing itself, unfolding its history without sending a signal that can arrive here. James Webb brings this reality into focus by showing how much complexity exists near that boundary. The closer observations push toward it, the clearer it becomes that the observable universe is already densely populated, richly structured, and far more active than earlier models anticipated. If this is true near the limit of observation, then whatever lies beyond is unlikely to be simple or sparse. Scale, then, is no longer just a question of distance. It becomes a question of access. The universe is not merely large. It is partially unreachable by the way it evolves. This reframes the meaning of discovery. Webb does not deliver a final map of the cosmos. It reveals that no such map is possible. Every deep field image is a narrow tunnel through time. Every measurement captures only what light has managed to preserve and deliver. The universe that exists now is different from the universe that is visible. What is seen is always delayed, always incomplete, always shaped by expansion. Observation becomes an act of reconstruction rather than direct inspection. Yet within these limits, something remarkable remains. From a small region of space, using light that has crossed billions of years, it is possible to infer a reality far larger than what can ever be observed directly. Patterns repeat. Laws remain consistent. Structure scales upward without apparent boundary. James Webb does not answer every question about the universe. Instead, it clarifies the nature of the questions themselves. Not where the universe ends, but why its full extent can never be reached. Not how much exists, but how little of it can ever be seen. The true scale of the universe is not defined by the furthest galaxy detected or the deepest image assembled. It is defined by the gap between what exists and what can be known. And that gap, illuminated but never closed, is one of the universe's most enduring features.